Hi, my name is Nitmin. Today I'm with another paper review. This paper considered as one of the most influential paper for the attention mechanism. The title of this paper is The Neural Machine Translation by Joint Learning to Align and Translate. So let's see what this paper brings to the table and why this paper considered as one of the most influential paper for the attention mechanism. What will happen if our model is going to compress the entire input sequence into a single fixed length context vector? Obviously it will lose some amount of information of the source text. So that was the problem we have in the encoder decoder machine translation models back in 2014 to 2015 time period. So the authors of this paper argued the use of this fixed length context vector. They said it was a bottleneck for the model's performance. So what if our model can dynamically focus on the relevant part of the source text while its machine translation process? In other words, what if we give a separate context vector for each target word? So they have proposed a solution. The key idea of the solution is to provide is to produce a unique context vector for every target word. So here's a graphical look of how the solution looks like. The main component of the solutions are the encoder, which is a bidirectional RNA, and the alignment model, which is a feed-forward neural network, and the context vector and the decoder. Okay, let's look at the each part one by one. As the encoder, they use a bidirectional recurrent neural network. That is because the bidirectional RNN is able to capture the context from the both sides of the sequence for its predictions. Okay, then we have the alignment model, which returns a score based on the previous output of the decoder and the current state coming from the encoder layer. If the score is higher, uh, the source word of the current state would become more important to the word we are going to generate, or the word we are going to predict. Okay, now we are having a relevant score. So as the next step, we will calculate weights using it. So these weights ultimately help us to find the attention we need to give for each source word while predicting the target word. So the next thing is the context vector. Since we are having all the weights we need, now we can get the context vector is specifically designed for generating our target word. Okay, as the final step, of course, we have the decoder. It will get the context vector, the previously predicted word, and the previous state from the encoder, and it's going to produce the conditional probability for the target word. Finally, we have completed the entire architecture the authors proposed. Okay, let's talk about the experimental setup. They trained both existing encoder-decoder model and their proposed solution. The model's vocabulary size is 30,000 and they use the blue square as the main evaluation metric. So the result is surprisingly good. The proposed model is way better than the existing encoder-decoder models, and the model showed a significant improvement when it comes to translating longer sentences, and this proved their dynamic context approach is really strong. So as we discussed, the proposed model is really good at translating longer sentences. So we are at the end. Let me summarize what we have discussed. This paper contributed to fix the fixed length context vector problem, and it helps to improve the translation quality of the longer sentences. And the most importantly, this paper influenced the authors of the attention paper to bring the attention mechanism to the stage.